The standard for high-end quantum computing currently relies on massive dilution refrigerators costing millions of dollars. This hardware is required because standard qubits store data in fragile probabilistic states. A single stray photon or a temperature shift of a few microdegrees causes decoherence, collapsing the state and erasing the computation. Topological quantum computation offers an alternative. It proposes storing information in a system's overarching geometry rather than in the energy states of individual particles. This approach can be physically manifested at room temperature using macroscopic magnetic fields. By utilizing the structural stability of these fields, it is possible to build a device that maintains topological states for under $100. To see how, we have to trace the path from Richard Feynman's sum over histories through the discrete shapes of atomic orbitals to the engineering of a functional ferrocell processor. Shifting from vulnerable particle states to macroscopic field geometry provides a structural defense against the decoherence that limits standard quantum hardware. In 1948, Richard Feynman introduced the path integral. He proposed that the behavior of a particle is determined by summing over every possible path it could take to get from point A to point B. Mathematically, this led to infinite values because the calculation included chaotic, divergent paths that never geometrically close. Physicists historically addressed these infinities using renormalization, a mathematical method of subtracting the problematic terms to reach a finite answer. Srinivasa Ramanujan's work on Mach theta functions provides a different framework for this sum. The Mach theta sum acts as a co-prime filter. It restricts the path integral to only those paths that share no common factors with the system's modulus, the paths that geometrically close on themselves. By focusing exclusively on these closed topological loops, the path integral becomes finite and well-defined without the need for external patches. This suggests that stable physical states are defined by closed topological paths from the very beginning. When this co-prime path geometry is applied to the Schrödinger equation, the results match the discrete shapes of atomic electron shells. Atomic orbitals, the S-sphere, P-dumbbell, D-clover, and F-flower, function as discrete winding geometries rather than simple probability clouds. The number of lobes in these shapes is determined by the angular momentum, which sets the exact number of nodes where the winding path must cross itself. Research published by Marcio Salcuni in 2025 demonstrated that these specific geometries are not exclusive to the subatomic scale. Using a scanning Hall sensor, Salcuni mapped macroscopic magnetic fields and found they spontaneously arrange into these same cloverleaf and flower-shaped patterns. The field locks into alternating polarities dictated by the overarching geometry, creating stable structures that can be navigated and measured. These shapes are scale-invariant topological structures, meaning they can be trapped and manipulated in the macroscopic world. The ferrocell is the physical medium used to make these field geometries visible and accessible. It consists of a 50-micron layer of ferrofluid, nanoscale magnetite suspended in oil, sealed between two optically flat glass plates. This orange geometric pattern arises as nanoparticles align with the magnetic field's topology. Under LED light, the chains reveal the field structure. This optical pattern is a direct map of the closed-loop paths, providing a visible instantiation of the co-prime path integral. The specific geometry is determined by the source magnet. Here, the field forms a symmetrical pattern around a central square magnet stack. In contrast, this horseshoe magnet traps the fluid in an entirely different set of arched field lines. Within the cell, information is encoded as a stable physical shape, where the topology of the field itself serves as the data carrier. The processor architecture is built in layers: a base electromagnet, an N52 permanent cube magnet, the ferrocell, an LED ring, and a camera for data retrieval. Writing information to the cell is a geometric operation. The permanent magnet maintains the field, while the angle of the LED ring selects which specific orbital shape becomes visible and active. To read the data, the camera captures the top-down view. Because the information is stored in the shape, the system can identify the state simply by counting the lobes of the pattern. Erasing the state is handled by the bottom electromagnet, which pulses a uniform field to reset the ferrofluid to a baseline, unpatterned state. By utilizing the structural stability of magnetic fields, this architecture can store and switch between geometric states without any cryogenic cooling. The construction uses standard materials, $20 for optically flat glass and $15 for spacers setting the 50-micron gap. Combined with $15 for ferrofluid, $16 for magnets and LEDs, and $4 for an Arduino, the hardware costs roughly $80 total. This architecture provides a way to store and retrieve topological states using off-the-shelf components and room temperature physics. Standard quantum computers rely on qubits that are easily disturbed by their environment. This geometric framework focuses on QMAGs, stable, multi-lobed magnetic field shapes. Standard qubits require near absolute zero temperatures because their energy-based states collapse under the slightest thermal noise. In a QMAG, the information is stored in the structural topology of the field. Each shape is a macroscopic superposition that is physically visible and measurable. Because the data is held in the global shape of the field, minor local vibrations or temperature fluctuations cannot easily alter the fundamental configuration. This makes geometric information topologically protected, allowing it to remain stable in environments where a standard qubit would fail. This architecture is the physical result of applying Ramanujan's closed coprime loops to the problem of path integral stability. Salconi's mapping confirmed that these mathematical shapes are real physical structures that can be manipulated at a macroscopic scale. By moving away from probabilistic particle states and towards stable field geometries, the barrier to exploring topological logic drops from $1 million lab to a kitchen table.